this video, I will be explaining my solution to problem 4 on the 2021 Spring HMMT Combinatorics round. So we're given this function here, and the problem is saying that when we apply this function to itself 3 times, we end back up at our starting point. And then we're also given this second condition that f of s minus s is not divisible by 3. Also, what this is saying is that the function f is going to take an input from the set of s, so it's going to take an input of one element from s, and then another element of s is going to be the output. And so that's going to be defined for all integers inside of s. So keep that in mind. That's what this is saying. Okay, so let's first examine our first condition here, right? So what this is saying, what this tells us essentially is that our cycle length of the function has to be a divisor of 3, right? And the reason being is because we're applying this function to itself 3 times, and then we're going back to our starting point. So, for example, I could have a cycle of length. So if I had a cycle of length 3, right? Cycle of length 3. Then I could have something like f of a is equal to b, f of b equals c, and f of c equals a. It takes me right back to the starting point. And this works fine, because if I plug in a for s here, then I'll have f of a in here. This evaluates to b, then I'll have f of b here, and that evaluates to c. And f of c takes me right back to where I started, a. So that's what I mean by cycle lengths, right? So I can also have a cycle of length 1, right? So cycles of length 3, these could possibly work fine, right? They don't necessarily violate the second condition either. So we could possibly have cycles of length 3, right? But what about cycles of length 1? Can we even have those? Well, if we had a cycle of length 1, then we just have something like f of a equals a, right? If we let a equal s, then we're obviously just going to have f of s equals s. And that clearly violates the second condition, because f of s minus s would evaluate to 0, and that is a divisor of 3, because 0 divided by 3 is 0. So we cannot have cycles of length 1. We must have cycles of length 3. So we have to have our cycles here of length 3. Okay, so now let's go back to that notation, right? F of a equals b, f of b equals c, and f of c takes us right back to a. So we can plug in all of these variables here for s in the second condition, right? So what do I mean by that? Well, let's plug in a here, right? So f of a minus a is not divisible by 3. So I can say that this is not congruent to 0 mod 3. So I can move the a over to this side, and then that essentially gives me that f of a is not congruent to a mod 3. But look, f of a is equal to b. So what that tells me is b is not congruent to a mod 3. And I can similarly repeat this pattern for all the other equations here, right? And then I can also go here. Okay, so cool. This is the first key piece of information that we needed. So we have all these different modular non-congruences, I guess you could say. And so this is some pretty important information, right? Now let's take a moment to first understand cycles, right? So here we have our path is going from A to B to C and back to A again, right? So we're going A, B, C, A. In reality, there are 6 factorial ways to arrange A, B, and C. So I can list those now, right? So A, then I could have something CB and then take me back to A. Or I could have something like B, C, A, B. I could have something like C, B, A, C. Maybe something like B, A, C, B. Right? Or I could have C, A, B, C. All of these are cycles we could possibly have. Right? It doesn't just have to be in this order necessarily. I just chose this because it's just like one of these possible cycles, right? Well, the thing about cycles is it doesn't really matter where you start. They're considered the same if they follow the same pattern. So, for example, I'm going from B to C and then to A again. Do I do that in any other cycle? Well, yeah, I do it in this cycle here, right? I go from B and then I go to C, and then it's predictable that I'm going to go to A again, because if I do, then my starting element here and this ending element are going to be the same. So these two cycles here are going to be the same, right? And do we see anything else? Yeah, this cycle is the same as those. And then similarly, we have that these blue cycles are also the same as each other. So there are 2 types of cycles. 2 types of cycles. You can either have the red type, where you go in this fashion, this distinct pattern here, Or you can have the blue type, where you go in this other distinct pattern here. So there are two different types of cycles we can choose from. So keep that in mind. This configuration I have here, this is just one of those two options. So we'll have to multiply by 2 over and over at the end, and you'll see what I mean. Okay, so now that we have that out of the way, there are two different types of cycles. Now we have a bunch of these non-congruences here, right? So let's try to organize the numbers 1 through 9 based on their modular residues, right? Mod 3. So that's just a fancy way of saying the remainder when they're divided by 3. So let's first take the multiples of 3. Those are just obviously going to be 3, 6, 9. Then we'll take the remainders when they're, we'll take the first residue, right? So like when they're divided by 3, the remainder is 1. And then when they're divided by 3, the remainder is 2. Cool. So what I'm going to count here is the number of ways to partition A, B, and C to satisfy this condition, right? These congruences here. So let's first start off by saying, let's let B be a multiple of 3. Let's just let it be a multiple of 3. It doesn't really matter, right? So if we let B be a multiple of 3, B has 3 choices. B can either be this, this, or this. So 3 possible choices for B. Without loss of generality, let's say B is 9. We chose B to be 9. Okay, now A cannot be a multiple of 3 also. A has to be different, right? Let's just assume that A is 8. Or let's assume that A is congruent to 2 mod 3, right? And then we choose 8 for A. We could have chosen any 3 of these options, but without loss of generality, I chose 8 for A. So now we have that out of the way. If A is congruent to 2 mod 3, then if we look here, we have A is congruent to 2 mod 3, and we also have B is congruent to 0 mod 3. So C has to be different from 0 and 2, so C must be congruent to 1 mod 3. Again, there are 3 choices for C. Without loss of generality, I'll just choose 1. So we're done with the first set we chose, right? The first set of ABC we chose was 1, 8, 9. But keep in mind, we have to cover all integers because it's defined for every element in S, right? We can't just cover 3. We have to cover all. So once we've selected these values for A, B, and C, we have to go in a second round. So now there are 2 choices for what A can be, right? A can be either one of these 2 options. Without loss of generality, let's say I choose 6, right? And then I can do the same for B. So let's say I choose 4 for B. And let's say I choose 2 for C. So my second set is going to be 2, 4, 6. And then my last set must be 3, 5, 7, because those are the only numbers remaining. So that's just implied, right? So 2 times 2 times 2 times 1 to the power of 3. So then I'm going to have 3, 5, and 7, I think, right? Yeah, 3, 5, 7. Okay. But now we have to also divide by 3 factorial, because I could have chosen any of these sets in any order, right? I chose 1, 8, 9 as my first set. I could have maybe chosen 2, 4, 6 as my first set, then maybe 1, 8, 9, and 3, 5, 7. Or I could have chosen 3, 5, 7 as my first set, then maybe 1, 8, 9, and then 2, 4, 6, right? We're overcounting those cases here. So we have to divide by that 3 factorial, because there are 3 factorial ways to arrange these sets amongst themselves. So that's important, right? So if we take this whole product here and we divide it by 3 factorial, then we get 36. But 36 is not our final answer, because remember what I mentioned about cycles, right? There are 2 flavors of cycles, the blue cycles we went over and the red cycles we went over. And for each of these sets that you chose here, each of these sets can either fall into the blue cycle category or the red cycle category. So there are 2 choices for them, right? So there are 2 choices for each of these sets as to which cycles they can be. So if each of these sets have 2 choices, then we have to multiply 36 by 2 times 2 times 2, or 36 times 8. So our final answer is just going to be 36 times 8, which is equal to 288, which is the final answer for this problem.